This is mathheals.com, where you can find more links to math and computer science YouTube videos. Let's take a look at extrema functions of two variables. Now, remember, relative extrema, relative min, relative max, refers to where you got a low point or a high point relative to what's around it. For example, not that I can draw it, but we have a 3D shape coming up here in some form. And here we got a high point relative to what's around it. This would be a relative max. Or if we got a low point relative to what's around it. Not that I can draw 3D, but use your imagination. That would be our low point. That's a relative min. So that's what we're finding here. Let me get rid of all that. There we go. Okay. Now the second partials test says let f have continuous second partial derivatives on an open region containing a point AB, for which our partial with respect to x of AB is equal to 0 and partial with respect to y of AB is equal to 0. So what that's saying is it says find your partials, set them equal to 0, and find out what A and B is. Then D is equal to our second partials multiplied together. So we take the partial with respect to x and take it again with respect to x times the partial with respect to y, take it again with respect to y, minus the partial with respect to x, and then we take it with respect to y squared. Now, if d is greater than 0 and our second partial is greater than 0, relative min. If d is greater than 0 and our second partial with respect to x in both times is less than 0, then it's relative max. If d is less than 0, then we got a saddle point. And the test is inconclusive if d is equal to 0. So let's take a look at this problem. We got f of xy is equal to x plus 4 squared plus y minus 2 squared. This says find any critical points and test for relative extrema. Well, we need to find our first partials. So the partial with respect to x, the y will be considered a constant, so this part's going to drop away. And so I'll take the power, put it out in front. What's inside the parentheses remains as is. Lower our power by 1, and then we multiply times derivative of what's inside the parentheses, which is just 1. So this gives us 2x plus 8. Then if we take the partial with respect to y, well, the x is a constant, so this part drops away. Take our power, put it out in front. What's inside the parentheses remains as is. Lower your power by 1, and then multiply times derivative of what's inside the parentheses, which is 1. Which gives us 2y minus 4. That's this part right here. Now we want to set these equal to 0. So 2x plus 8 is equal to 0. And 2y minus 4 is equal to 0. So we've got 2x is equal to negative 8, or x is equal to negative 4. Divide both sides by 2. Take the negative 4 over, becomes a positive 4. Divide both sides by 2, and we get y is equal to a positive 2. So we're going to be taking a look at this x value and this y value. Those are our critical point. Now we need to find our second partials we have listed here. So let's do that. I'm going to take the partial with respect to x, which was 2x plus 8, and take it again with respect to x, which gives us 2. We'll take the partial with respect to y, which is 2y minus 4, and take it again with respect to y, which would give us 2. And we're going to take our partial with respect to x and take the partial of it with respect to y, which would give us 0. And D is going to equal to these two partials multiplied together minus this partial squared, second partial squared. So we got 2 times 2 minus 0 squared, which gives us D is equal to 4. Okay. Well, we got our, this is our critical point right here. Let's see. D is greater than 0. Well, D is greater than 0, so it's going to be either 1 or 2. And our second partial with respect to x up here is equal to 2, which is greater than 0. So it tells us it's a relative min. At negative 4, 2, and then f of negative 4, 2. So I'll have relative min at negative 4, 2, and if I go up here and put in negative 4 for the x and 2 for the y, I get negative 4 plus 4, which is 0, 0 squared 0. If I put 2 in here, 2 minus 2 is 0, 0 squared is 0. 0 plus 0 gives us 0. So that's our relative min. Let's do our next problem. Scroll down a little bit. Minus 8y plus 2. Okay. Well, we need to find our first partials. So partial with respect to x. Again, the y and the numbers like constants, so they drop away. So x squared becomes 2x. Y squared's gone. Derivative of 4x is 4. The negative 8y disappears and 2 disappears. Partial with respect to y. Well, the x squared's gone. Derivative of y squared is 2y. 4x is gone. Derivative of negative 8y is negative 8. And 2 disappears. Then we're going to set each one of those equal to 0. And we get 2x is equal to negative 4. Divide both sides by 2. And we get x equals negative 2. Here, take negative 8 over, becomes a positive 8. Divide both sides by 2. And we get y is equal to 4. So we're going to be dealing with negative 2, 4, and our z part, which we get by plugging in negative 2 for the x and y, or 4 for the y. Okay, let's see what this is, though. We're going to take our 2x plus 4 and take the partial of it again with respect to x, which gives us 2. We're going to take 2y minus 8 and take the partial of it again with respect to y, which is 2. And then we'll take our first partial with respect to x and take it with respect to y. So this 2x plus 4, if I take derivative with respect to y, it just gives us 0. So d is going to equal to this right here. So we're going to have 2 times 2 minus 0 squared, or d is equal to 4. Now let's do the relative min again. So relative min. Reason why is because this is positive and this is positive, which is our first one here, relative min. Well, if I put negative 2 and 4 up here, let's see what in the world I got. F of negative 2, 4. We're going to have negative 2 squared plus 4 squared plus 4 times x, which is negative 2, minus 8 times y, which is 4, plus 2. So that gives us 4 plus 16 minus 8 minus 32 plus 2, which gives us 20 minus 8, which 20 minus 8 is 12. Negative 32 plus 2 is negative 30, which gives us negative 18, I believe. And that would be our relative min. Probably have room for that one. Let's see. Got f of xy is equal to negative x squared minus 3y squared. Those being negative probably is going to tell you something. Plus 8x minus 12y plus 3. And let's find our first partials. So the partial derivative with respect to x gives us negative 2x. The negative 3y squared drops away because we treat it as a constant. Derivative of 8x is 8. Negative 12y disappears and 3 disappears. Partial respect to y. The negative x squared drops away. The derivative of negative 3y squared gives us negative 6y. 8x drops away, and derivative of negative 12y is negative 12. And 3 drops away. Set each one of those equal to 0. And take negative 2x to the right side, becomes a positive 2x. Divide both sides by 2, and we get x is equal to 4. Here, take negative 6y to the right side, and it becomes a positive 6y. Divide both sides by 6, and we get y is equal to negative 2. Well, we need our second partials. So I'm going to take negative 2x plus 8 and take it again with respect to x, our partial with respect to x, which gives us negative 2. We're going to take negative 6y minus 12, take it again with respect to y. That gives us negative 6. And then the partial of negative 2x plus 8 with respect to y gives us 0. Okay. Well, d is going to equal to this right here. So we're going to take negative 2 times negative 6 minus 0 squared, which gives us 12. Now here, this is negative and this is positive. So if I come over here, okay, d is positive, and then this is negative, that's 2, relative max. So we're going to have relative max at 4, negative 2, and then we'll plug 4, negative 2 in to get our z. So we got 4 f of 4, negative 2, and I'll do that over here on the side. 4, negative 2. So we're going to have negative 4 squared minus 3 times negative 2 squared plus 8 times 4 minus 12 times negative 2 plus 3, which gives us negative 16. Negative 2 squared is 4 times negative 3 is negative 12. 8 times 4 is 32 plus 24 plus 3, which gives us negative 28. 32 plus 24 is 56, plus 3 is 59. 59 minus 28 gives us 31. So our relative max is at 4, negative 2, 31. Assuming I did my basic math correct, which is always kind of iffy. Let me double check myself. Okay, negative 16. 4, negative 12, that's negative 28, which gives me 4, 28, 31. Yeah, looks right. Okay. Let me save that page. How's this again? Extrema functions of two variables. Extrema of functions of two variables. Page 01.pdf. Okay, let's look at this. Now sometimes when you're working these problems, some of them you use the formula, and some of them just common sense kind of tells you what the answer is going to be. So we'll see that with this problem. Okay. So partial is back to x. Remember, this is the same as 3x squared plus y squared to the 1/2. And we got parentheses to a power. And it's always the same. You take a power, put it out in front. What's inside your parentheses remains as is. You'll lower your power by 1. So we've got 1/2 minus 1 times the derivative of what's inside the parentheses with respect to x, because we're taking the partial with respect to x. So the derivative of that gives us 6x. Well, that gives us 1/2 3x squared plus y squared to the negative 1/2 times 6x. 1/2 times 6 is 3, so we're going to have 3x over, and I'll take this negative 1/2 down to the denominator. So we've got 3x squared plus y squared to the 1/2. So we're going to have 3x over the square root of 3x squared plus y squared. Okay, partial with respect to y. Again, take a power, put it out in front. What's inside the parentheses remains as is. Lower a power by 1. And then we multiply times the derivative of what's inside the parentheses with respect to y, which is 2y. Well, the 1/2 times 2 cancels. We're left with the y on top. And down below we're going to have 3x squared plus y squared to the 1/2. Which gives us y over the square root of 3x squared plus y squared. Now for your critical value, you not only set this equal to 0, but if you have a fraction, you set the top part equal to 0, and you set the bottom part equal to 0. And same thing over here. We'll set the top part equal to 0 and the bottom part equal to 0. Well, this 3x equal to 0 implies x is equal to 0. Well, divide both sides by 3. And y is equal to 0 here, so that's one of our critical points. And actually, that's the only values we can put in for x and y that cause this to be true. So our critical point is 0, 0. Zero, 0, and f of 0, 0. Well, if I put 0 in for x and 0 in for y, 0 squared is 0 times 3 is 0 plus 0 squared is 0, square root of 0 is 0. So z is going to equal to 0. But let's think what this could be. Without finding the second partials, what happens when you square something? Well, it becomes positive or 0. So if I would have put in a 1 here for the x, or a negative 1, then that gives me a positive 1. So no matter what, when I put anything in for the x and actually for the y also, my lowest value is going to be this right here, which tells me that's a relative min. Now you're going to find that some of the problems in this section, you'll be able to look at them and just kind of see whether they're relative min, relative max. This is another one you can just look at. Okay, so we got f of xy is equal to 2 minus absolute value of x plus 3 minus absolute value of y minus 1. Now, the book kind of implies that some of these you can just look at and you can see what the point is. And you can. When you think about what the absolute value does, it makes whatever's inside positive, or it can be 0. So no matter what, this is going to be 0 or positive. So the highest value it can be is 2 minus 0 minus 0 at x equals negative 3 and y is equal to 1, which is going to be a relative max. But let's at least do the derivative. So take the partials back to x. The 2 disappears. The absolute value of y minus 1 will disappear. And here we got negative. Now the derivative of an absolute value, we don't see this a whole lot. Let me write the formula over here. I don't know why it's not very popular to see in exercises. But the derivative of the absolute value is equal to the derivative of the absolute value of u is equal to u over the absolute value of u times u prime, assuming there's more than a single x in there. Okay, so the negative I'll just put up on top, this negative out in front. And what's inside the absolute value is your u, so we'll have x plus 3 up here, and we'll have the absolute value of x plus 3 down here. Times the derivative of what's inside the parentheses, but derivative of x plus 3 is just 1. So that's going to give us negative x minus 3 over the absolute value of x plus 3. Now take the partials back to y. Same idea. We'll take that negative right here, put it up on top, and the u is what's inside the absolute value. So we've got y minus 1 here, and the absolute value of y minus 1 here, times the derivative of y minus 1, which is just 1. So that's going to give us negative y plus 1 over the absolute value of y minus 1. Now, again, we have a fraction, so it's that top part equals 0 and the bottom part equal to 0. Like this. Now here I take negative x over, and we get negative 3 is equal to x, which is actually the same thing this would give us. Here I'll take negative y over, and we get y is equal to 1, which is the same thing as this would give us. So our critical point is going to be at negative 3, 1, and then f of negative 3, 1. Well, let's think what we already said. We said that the largest value can be is 2. So this is going to be a relative max at this value here. Now if I were to plug negative 3 in for the x, negative 3 plus 3 is 0, absolute value of 0 is 0. If I plug 1 in for the y, 1 minus 1 is 0, absolute value of 0 is 0. So the z would be equal to 2. So our relative max is going to be negative 3, 1, 2. And that's our answer. Let's save that. Like I say, some of these you can just look at. You don't have to actually go through all the steps. Okay, let's take a look at this one. This one's kind of an interesting graph, so we'll take a look at the graph of this after we find it. We got f of xy is equal to xy minus 2x. And come up here. Same steps. We'll find our partials back to x. Y is a constant, so it remains xy. The derivative of x is 1, so 1 times y is y. Minus, and then derivative of 2x is 2. Then the partials back to y. The xy, the x is a constant. The derivative of y is 1. X times 1 is x. And then that drops away. So we'll set each of these equal to 0. Y minus 2 is equal to 0, and x is equal to 0. And we've got y is equal to 2, and x is equal to 0. Now these are going to be our critical point, but let's come over here and find our second partials. So we'll take the derivative of y minus 2 with respect to x, which gives us 0. We'll take the partial with respect to y of x, and that gives us 0. And then the partial of y minus 2 with respect to y gives us 1. So d is equal to these two, like that, which is going to give us 0 times 0 minus 1 squared, which gives us negative 1. That's this one. If d is less than 0, then we found a saddle point. So we're going to have a saddle point at x is 0, y is 2, and see what z is. If I put 0 in for the x and 2 in for the y, that's 0. If I put 0 here, 2 times 0 is 0, 0 minus 0 is 0. So that would be our saddle point. Let's graph this. Choose window, 3 dimensions, and choose equation explicit. And we got xy minus 2x. And let me click OK. Then view axis. Now if I rotate it, you see a saddle point there. It's coming up, increasing, hits a high point here, and then starts decreasing. But coming from this angle, it's decreasing, hits a low point, and then starts increasing. So it's both a min and max at the same point. Now let me draw a point there just so you can see it specifically. This is 0, 2, 0. So do equation, point, Cartesian, 0, 2, 0. I'll make dot size 4 and click OK. As I rotate it, you can see the saddle point. Yep, there it goes. Saddle points are kind of interesting. Of course, their name comes from the fact that they look like a saddle. Okay, let's take a look at this one. 7, we got f of xy is equal to e to the x cosine y. And let's find our partials with respect to x. Well, the cosine y is a constant part, so it just remains. And derivative of e to the x is e to the x. So partial with respect to x is e to the x cosine y. Now, partial with respect to y. The e to the x is a constant portion, so it remains. And derivative of cosine is negative sine. So we're going to have negative e to the x sine y. I put the negative clear out in front. Well, now we're going to set these equal to 0. There we go. And negative e to the x sine y is equal to 0. Now, here we got something factored, a product. This times this. So, zero factor property from college algebra, we can set each one of them equal to 0. I'll set e to the x equal to 0 and cosine y is equal to 0. And over here, I'll do the same thing. I'll set negative e to the x equals 0 and sine y is equal to 0. Now, e to the x is equal to 0. This is an exponential equation, and our steps are to get the part with the variable and the exponent by itself, which it is. There's no numbers in front of it, no numbers after it. Take natural log of both sides. If we take natural log of both sides, we're going to have a natural log of 0, which we can't have. So that drops away. And this one would also drop away. You can never have e to the, or anything to the x power equal to 0. Now here, we got cosine y is equal to 0 and sine y is equal to 0. What this is saying is we go around a unit circle, we're looking where cosine is equal to 0 and sine is equal to 0 at the same time, which doesn't exist. So there's no critical point, which means there's no relative min, no relative max. So no relative extrema. There's no use to go on further. If we don't actually have a point, then that's it. Okay, let's look at this one. And save this. Then we'll there we go. Let's take a look at this one. We got f of x, y, z is equal to x minus 2 squared plus y minus 1, y plus 1 squared plus z minus 5 squared. And it says find the critical points of the function, and from the form of the function determine whether it's relative max or relative min. So they don't want you to do anything but look at the form of it. So if we find a partial with respect to x, the y and z would drop away, and the derivative of x minus 2 squared, take your power, put it out in front. That lower your power by 1, multiplied times the derivative of what's inside of parentheses, which is 1. Partial with respect to y, take my power, put it out in front. Lower my power by 1 times the derivative of what's inside of parentheses, which is 1. And partial with respect to z. Take your power, put it out in front. Lower your power by 1 times the derivative of what's inside the parentheses. So this gives us 2x minus 4, and we'll set it equal to 0. And this gives us 2y plus 2, and we'll set it equal to 0. And this is 2z minus 10, and we'll set it equal to 0. So we got 2x is equal to 4, or x is equal to 2. 2y is equal to negative 2, or y is equal to negative 1. And 2z is equal to 10, or z is equal to 5. So, these are all squared, which means that this right here, 2 minus 2 is giving me 0. Negative 1, negative 1 plus 1 is 0. And 5 minus 5 is 0. That's the smallest it can be, which means this is going to be a relative min at 2, negative 1, 5, and then f of 2, negative 1, and 5. So I got 2, negative 1, 5, and if I plug those in, 2 minus 2 is 0, negative 1 plus 1 is 0, 5 minus 5 is 0, so this will be 0. Now, in some books they don't represent as that with parentheses around like that. They'll say there's a relative min of 0 at 2, negative 1, 5. So it kind of depends on how you want to write it. Let me save that. Now let's take a look at absolute extrema. This is the absolute min, absolute max, your highest point and your lowest point. Now, first thing we'd want to do is we want to find our first partial, set them equal to 0, and find the critical points, just like we did before. You have to make sure they are in the region specified. Then we want to find the high and low points of the boundaries. Plug in either the x or y, and then take the derivative. We want to find the intersections. Then plug all the above into the function. Largest value is your absolute maximum point. Smallest value is your absolute minimum point. Like, let's take a look at this one. We got f of xy is equal to x squared plus xy. And the region is when the x values are between negative 3 and 3, and the y values are between negative 1 and 1. Well, if I just think of the x values and the y values, negative 3 and 3, and then our y values are negative 1 and 1. This would form what am I doing wrong? Okay, I'm not must be clicking it there. This is forming this little rectangle right here. Now these are straight lines, so this is nothing real exciting about this, but these do not have to be straight lines. If I look at this at a side view, instead of it being a straight line, it might look like this. Now looking from the top here, it might look like that, but from the side view, it may look like this, which means that this would be a high point here. This would be a max. So we have to worry about more than just the intersections here. Now the intersections, I got my picture here. This one will be negative 3, 1. This one will be 3, 1. This one will be 3, negative 1. And this one will be negative 3, negative 1. So we're going to need to worry about those. But first thing, they say find the first partial, set them equal to 0, and find the critical points. Okay, well my partial is back to x. Again, the y we treat as a constant, so this becomes 2x plus y. Partial is respect to y. The x squared drops away, and then xy just becomes x. So I set each one of these equal to 0. So we got 2x plus y is equal to 0, and x is equal to 0. Well, x is equal to 0, and if I plug that in over here, I got 2 times 0, which implies y is equal to 0. So our critical point is going to be 0, 0 in terms of our x and y. So that's one of them. Now we know we're in 3 dimensions, so we'll have the z on there eventually, but we'll just write the x and y to begin with. Well, that's what this first one says. And it says make sure they're in the region. Well, 0, 0 is right here in the middle, so it's definitely in this region. Now it says find the high and low points of the boundaries. Plug in either x or y and then take derivative. I shouldn't say or, it should be and. Well, if we this is our first item. Our second item here, we're going to plug in our extreme values. Plug in negative 3. We'll plug in 3, and we'll plug in y equals negative 1, and y is equal to positive 1. Okay, we're going to plug those into our original function here. So when I plug this in, the x equals negative 3, we're going to end up with, put negative 3 here and we get 9. Put negative 3 here and we get minus 3y. And now this is a function in terms of y. So if I were to take the derivative of this, the derivative of that is negative 3. So there is no critical point here, so there is no high point, low point. So it's no critical point. It's kind of sloppy, isn't it? Now if I plug in x equals 3, then we're going to have a function in terms of y. So put 3 in for the x. So 3 squared is 9. And put 3 here, and we get 9 plus 3y. Now if I take the derivative of that, that would give us 3, which is, again, there's no critical point. Now if I plug in y is equal to negative 1, we're going to have a function in terms of x's. So we're going to have x squared, and if I put negative 1 here, negative 1 times x is negative x. Now if I take the derivative of this, that gives us 2x minus 1. And we can actually set that equal to 0. So 2x minus 1 equal to 0, and we get 2x is equal to 1, and x is equal to 1/2. Now I say to find the high and low points, but we don't actually need to find that. We have our point we're going to plug in. Let's go ahead and do 1. If I put 1 in for the y, I'm going to have f of x is equal to x squared. And if I put 1 in for the y here, 1 times x is x, which gives us 2x plus 1. So I'll go ahead and set that equal to 0. And we got 2x is equal to negative 1, or x is equal to negative 1/2. Okay. Our first point we're going to be plugging in is this one right here. Now we also have this one, 1/2, negative 1. And we also have negative 1/2 and positive 1. So we're going to be plugging those in too. Find the intersections. Well, I've identified those up here. That was this negative 3, 1, 3, 1, negative 3, negative 1, 3, negative 1. So those are intersections. Let me write those down again. So I got negative 3, negative 1, and negative 3, positive 1, 3 and 1, and 3 and negative 1. Okay. Well, we're going to take all of those now and plug them in and see which ones gives our largest and our smallest. What was our critical point? Critical point was 0, 0. Okay, so we want to plug that into our original function. What was our original function? X squared. So we're going to have 0 squared plus 0 times 0, which gives us 0. Okay, then our next point was 1/2, negative 1. So f of 1/2, negative 1, we're going to have 1/2 squared plus x times y, x times y. So we'll have 1/2 times negative 1, which gives us 1/4 minus 1/2, which gives us 1/4 minus 2/4, which is negative 1/4. Okay, our next one is negative 1/2, 1. So we got f of negative 1/2, 1. So we're going to have negative 1/2 squared plus negative 1/2 times a positive 1, which gives us 1/4 minus 1/2, which again gives us negative 1/4. Okay, now let's plug in our intersections here. So we've got negative 3 and negative 1. So f of negative 3, negative 1, we're going to have negative 3 squared plus negative 3 times negative 1, which gives us 12. Yeah, 12. And then we're going to have negative 3, positive 1. So f of negative 3, positive 1. We're going to have negative 3 squared. We're plugging in at x squared plus xy, our original function. And we have negative 3 times 1, which gives us 6. And then we'll plug in 3, negative 1. So f of 3, negative 1 is going to give us 3 squared plus 3 times negative 1, which is 9 minus 3, which is 6. And then 3 and positive 1, which is going to give us, we'll plug it in, we're going to have 3 squared plus 3 times 1, which gives us 12. Okay, well, our smallest values are these two right here. So these are our absolute mins. Those are our smallest values. And our 12s here are absolute maxes. And I'm out of room here, so let me write it up here. It's my answer. So my absolute min is going to be at 1/2, -1, -1/4, and 1/2, -1/2, sorry, 1 and -1/4. And then we'll have our absolute max, which is -3, -1, and 12, and 3, 1, and 12. Okay, now let's graph this. Get x squared plus xy. So you got equation, explicit, x squared plus xy. Now our x low, x high, y low, and y high, I'm going to get those so they match here. -3 to 3. So -3 to 3, -1 to 1. And I'll click OK. Now I'm going to do View, Axes, Axes. And let me put the points on there that we found. So my absolute min. So do equation, point, Cartesian. And I got 0.5, -1, and -0.25, -1/4. And I'll make it 4, and solid, and click OK. And see, there's our one of our low points. Now the equation, point, Cartesian. Now choose our other one. Our other one was -0.5, -0.5, 1, and -0.25. And click OK. And you can see our that's our absolute mins there. Now our absolute max was -3, -1, 12. So do equation, point, Cartesian, -3, -1, 12. And our other one, equation, point, Cartesian, 3, 1, 12. And as I rotate it, makes perfect sense when I say those are absolute max and those are absolute min. You can see it with the example. Now sometimes they're kind of tricky to find, you know, the intersections like this, to find out the maximum, minimum. But each problem's kind of different in that regard. I wish I could give you a step-by-step that works 100% of the time, but each one you may have to treat a little bit differently. Some of them give you the points of vertices of a triangle, and then you have to take those individual points and come up with the equation of the line for each line. Let me save that. And go scream at my wife to why she's got TV so loud. Because I know nobody's sitting there watching it. It's turned it up and left. Okay, let me stop the recorders.